welcome to everyone. I'm Mike Erickson. I'm the Associate Vice President for Community Engagement at Internet2. And I'd like to welcome you all to today's webinar. It's entitled The Pandemic and 5G, the Lasting Impact and New Challenges for Our Communication Networks. This event is being recorded and we will post it along with the slides on the i2 Online website. We reserved time at the end of the presentation for questions, but feel free to post them in the Q&A function of your Zoom window. The chat function is also available for all of you to post comments for group discussion. We are pleased to have with us today Todd Sizer, Vice President of the Wireless Research Program at Nokia Bell Labs, for a discussion on the challenges of new requirements, increased reliance, and the continued growing demand on our communication networks posed by the coming 5G industrial revolution. So welcome, Todd.
Well, thank you, Mike, and thanks to all of you for joining. I would like to share with you our thoughts at Bell Labs on the change, the impact, the acceleration that we're seeing in the communication networks as a result of the pandemic, as well as some of our thoughts and some of our research that we're doing to try to address these challenges. So immediately following the pandemic in 2020, we at Nokia were able to see through our sensing changes in network traffic. And so we almost immediately, within the first weeks of the pandemic and the lockdown, we saw 30 to 50% increase in traffic. Traffic is increasing quickly already, but this was somewhat abrupt. We saw an increase of nearly 100% in entertainment traffic, as indicated by Netflix traffic, and video conferencing, obviously driven by more of us doing work from home, our kids doing learning from home. And then, of course, to entertain the kids that now couldn't see their buddies. And we saw a dramatic increase in gaming traffic. So the implications of this were clearly there was an initial network surge due to the entertainment demand that I mentioned. But there was a surge that was related to changes in the way that we work, the way that we learn. And I would argue those changes to some degree will be with us now for a very long time. Many of us are looking at a blended work where some work from home, some from the office. And so this surge that we saw initially, we believe will remain. We saw as a side result that housing markets surged as well. We looked at the places that we were living and realized that now they had to be a place for not only for us to live, but also a place for us to work and learn. And so the houses that we were living in, the apartments we were living in, just simply weren't suitable anymore. And so we saw a housing surge, as well as people moving out of cities where remote work via work and learn from home is now the norm, not the exception. We unfortunately saw a dramatic increase in DDoS attacks, so security attacks, denial of service attacks. And so in this time when we see more importance in our communication, it's more essential. Security has never been more important, and so we need to redouble our efforts in that area. And I would argue that, as we've seen, and in fact, I would argue this has happened even before the pandemic, but there was an exclamation point put on it during the pandemic, that the broadband networks, residential networks that connect people to each other and to their world, are now critical infrastructure. We've seen that in many different ways, one being the reliance for news that many of us get from our connections. Paper newspapers are disappearing and being supplanted by online news. And for those of us that don't have a broadband connection, we are at a disadvantage. And so I would argue that broadband residentials are now critical infrastructure. We're seeing this here in the United States with recent initiatives from the White House as well. The connections that we get are essential, as I mentioned, and with those essential connections come a change in what the expectations are of people. People are not happy having best effort connection. They need a reliable connection. This is the way they interact with the world. This is the way they learn. And so those communication expectations have changed, and I argue that they have changed forever. We will never be going back. So three other items that we see as being rather fundamental and changed. Clearly, the pandemic has changed the expectations for communications. They are now critical. They are now essential. But the other transitions that we're seeing is that the smartphone, the limit of the smartphone is that we essentially, with voice, video, and web surfing, we have reached a limit of the value that we can create out of that model. And as we look forward as an industry, the new applications, the new opportunities are in industrialization and automation and the value paradigms that are associated with that. These are the new things that leverage the ubiquity of connection that the networks of today have provided, but now with different requirements, different expectations as well for these industrial applications. At the same time, we are reaching the physical limit of current networks. Shannon's limit, which was Claude Shannon 70 years ago at Bell Labs, told us what the limit was in terms of how much information you can send over a physical medium. It could be wireless, it could be copper. In this case, I'm talking about fiber. And we have essentially reached that physical limit of how much information we can put on a single color of light on an optical fiber already. And so now we have a fundamental change on the way that we need to communicate. And we are looking at a new distributed architecture for that. And I'll talk about that today. And finally, the proliferation of connection, the proliferation of fiber and wireless connections mean that the number of physical connections is just simply exploding. We're seeing this with the number of cell sites that are going up, the amount of fiber that's being put in the ground. And the operational complexity of that network is now so complex that we need to employ a lot more sensing and automation in order to make those systems perform as they should. So we need a new automated solution for this increasingly complex web of fiber and wireless connections. So what I'd like to share with you today are three of what we see as the key industrial challenges that are facing us today. I'm going to talk primarily on the transport network today, so optical networks. Optical networks are the backbone of the internet, as all of you know very well. Fiber comes to within 100 meters, I would argue, just about every machine or person that we wish to connect. The last few meters being over a 5G or a Wi-Fi connection, if you're not already directly connected via your PON or your direct IP connection. So I'd like to talk about optical capacity, which is growing dramatically. I'd like to talk to you about processing and the fact that more cloud processing is changing the way that we connect and communicate and interpret data and the challenges this brings. And then I'd like to talk to you about deterministic networks. Deterministic networks as to be compared with best effort networks, which I would argue are what we essentially have today. And the transition to deterministic networks is one of the more fundamental changes that we see having to bring to the market and architect in the next decade. So first, optical capacity. So the optical capacity story is actually one of Hero's work. If you look at the line, this is a complex slide, a graph here, but let me try to talk you through it. So if you look at the line that's marked per wavelength or per lambda interface rate, you see that this is the amount of information we can put in gigabits per second. on a single color of light. And you see for the past 40 years, we've done quite a remarkable job of growing that at 20% per year. Imagine if we were able to get batteries to grow by 20% per year. It's really heroes work. What we saw in the 90s was the application of WDM, so use of wavelength division multiplexing. What does that mean? That's multiple wavelengths on a single optical fiber that travels simultaneously with different data on the different colors of light. And so if you gang together 100 of them, as shown, the total capacity on a fiber increases. But after we filled up the band that was available to us in around 2000, we essentially have been tracking the total capacity on a fiber, which is the top line, with 100 times the capacity on a single wavelength, which is the bottom. And so we continue that trend. And so what I show here are the next generation systems from Nokia. It's called the Nokia PSC, or Photonics Service Engine. And we're looking to provide systems of up to a terabit on a single wavelength in the coming year or two. And like I said, I consider that heroes work. My team has been involved in a lot of that, driving the coherent revolution, particularly in the past decade. However, the other trend that's happening is Moore's law. And while the 20% per year that we're seeing a growth of capacity on the optical fiber is heroes work, the growth in the number of transistors on a die and relating that to information and information sharing that needs to happen, that's growing by 60% per year. And so if you look at traffic in our networks, they are indeed increasing by 40 to 60% per year, tracking very closely to what Moore's law is doing. And so this has posed a great challenge. We have the fact that our ability to transmit information on an optical fiber is growing 20% per year, but the demand, the need, as proliferation of use is happening, as more and more people are connected to the internet, as the applications that we use benefit from this growth in Moore's law, all of this is driving this enormous capacity increase, an increase that I would argue is also not going to slow down. If anything, it's going to increase. And in fact, we're seeing that already for some applications, upwards of 100% or more per year growth that we're seeing. So we had one step along the path. We doubled the amount of wavelengths that we were able to provide at a cover. It was a band called the L band. In optics, we have been transmitting information on what's called the C band. And so first products to do both at the same time came out, and that was great. That was a factor 2 increased capacity. But of course, if you project that forward, we really think that we need to be building systems where we have upwards of a petabit per second on a single fiber in the future. And I'll talk to that issue in a second on how we're going to get there. I would also indicate, if you look at the graph on the right, you see a couple of things that are going to echo with what I'll tell you in the future. And one is that you see around, and all of us remember this with the Intel processors that we purchased for our computers at home. So around 2000, we started to see the advertisements from Intel stop talking about faster and faster processors. So 4 gigacycle processors were what people were talking about. And we really haven't seen that continue. I mean, we haven't seen them advertise a 20 gigahertz processor, for example. And instead, what we saw, as shown in black on the bottom, is we saw now multiple cores. This is multiple different instances of a computer within the same die, within the same housing, within the same computer. And so the way that we kept up with, in this case, computing capacity, was not by going faster, but going more parallel, going in multiple cores. And as I said, you will see that we are looking to echo some of that in our direction, in the direction that we're going as well. So Claude Shannon illustrated with his famous Shannons Law, which is shown at the top, that there really are only three different ways that you can increase capacity. The first is spectral efficiency, and that is how much information you can put on a single color of light at the given time. And as I indicated before, with probabilistic constellation, which is a technology that Bell Labs and Nokia were first to roll out back in 2018, we have the ability to adjust capacity to meet perfectly to within Shannon's, what I call the economic Shannon's limit. What do I mean by that? I mean that if we were to get ever closer, the last dB or so, it would cost an exorbitant amount. And so, in fact, the economic limit we essentially are at today, with the benefit of probabilistic constellation, which adjusts the capacity, the amount of information you can send, depending on how long the fiber is or how much loss you see in that optical fiber. So we can right match with nearly infinite resolution, the amount of information over a given length. The second way that we're looking at expanding capacity, and I mentioned this in the C+L solution, is by broadening the bandwidth. And are there systems and amplifiers that you can use that provide ever widening bandwidths? And certainly this is an interesting area that we're exploring. But I would note that a doubling of capacity in bandwidth, or doubling of bandwidth would cause a doubling of capacity. That's great stuff. But if the capacity demand in the network is 60% per year, then you've solved the problem for 2 or 3 years, but you haven't solved the problem longer than that. And so we need to use that, but we also need other things. And those other things, we argue, are space. That is, we need to have parallel channels to send information on not one fiber, but on either many fibers, or in a single fiber on multiple cores. You see 2 here on the bottom and 8 here at the bottom. Or on multimode fibers, where we have different information on the different modes that are going in the optical fiber at a time. Again, this is space. These are multiple instances. Again, echoing what I showed you on the previous slide of multiple cores being able to provide enhanced capacity as well. So our vision of the future is the way that we're going to get to a petabit per second system is if we develop, and we have developed, solutions that can give you upwards of a terabit per second or even more, slightly more, on a single color of light. The way that we will get to a petabit per second is by multiplexing that with multiple versions of wavelengths, so more spectrum, more wavelengths running at the same time, and space, multiple modes. And by ganging all those together, we see this as the most attractive path to meet the capacity demands of our networks. So one example is from a couple of years ago, is one from my team where we developed a new type of optical amplifier. So since the 90s, we have used an amplifier called an erbium doped fiber amplifier as the medium to amplify optical signals, which is essential for communication. And it's worked remarkably well, really remarkably well. And but it has a limited band, and that band is about the same dimension as the C band, which is shown in the center bottom. What we have developed in the labs and foundry that are in my team in Paris is a new semiconductor optical amplifier, which has a much wider bandwidth, so it can carry not only a C band, not only the C, which is for communication band, but also lower than that, the L band, and shorter than that, the S band. And by carrying all 3 bands at once and using that probabilistic constellation power in order to adjust the speed on each color, depending on the losses that we see, we were able to get in excess of 100 terabits per second on a single optical fiber. So a good step along the path. But as you see, it's a tripling, which is, again, heroes work, but it's going to be a technology that will not solve the larger problems that we have. So move to spatial division multiplexing, the use of different spatial channels. And there are several different ways of doing that. We can use single mode fibers, so fibers like we have today, either in a ribbon, which I expect you'll see to a great degree, or you pile them all next to each other in a cable, and so you have multiple single mode fibers in a cable. This is what you have undersea today. Or you have larger ones that have a more significant spacing between them, or new ones that I'll tell you about today, which are multi-core fiber. So you have multiple cores in a fiber, or multimode fiber. So you have a larger central core, and so it supports not just a single mode, but multiple modes, and we'll talk about that. And then we have a new solution that we're excited about called a coupled core multi-core fiber, where the cores there are multiple cores, but they are so close to each other, they actually do couple to each other. And in both the multimode case and the coupled core case, because there's coupling, if you transmit information on one of those cores or one of those modes, and it travels down up a optical fiber, it's necessarily going to mix with others. And so borrowing from the MIMO technology in wireless, which is prevalent in 4G and 5G standards, which use multiple antennas to transmit different information out of each antenna to a remote site, we're echoing that in this case, where we're applying those MIMO algorithms to undo the mixing that happens between one core and another in these coupled core or multi-mode fiber systems. In fact, we might also see some coupling in multi-core fiber if we have shared amplifiers or shared equipment. So the MIMO processing that we have become expert with in driving next generation wireless systems, we are now reusing in new ways in the optical fiber. And given the amount of coupling as shown in the bottom graph in the bottom, you can decide to either need MIMO or not need MIMO. So let me first talk about two of these. I'll talk about coupled core and some recent results that we have there, and then we'll shift to multimode fiber experiments, which we have done, and to share some of the things that we're seeing here. So this experiment we did in Italy on a somewhat a longer test bed using 7 cores that were closely coupled. We also at the same time did experiments with 4 and 1 core as comparison, but I'm going to be talking mostly about this 7-core multi-core fiber. The different information was put into this multi-core fiber, different channels, in our case 7. They mix along this multi-core coupled core fiber and then are demultiplexed at the back end. We then need to do MIMO processing in order to undo that coupling that I mentioned before. We actually built a real-time transceiver to do that. It's somewhat complex. Let's not forget that in optics, as opposed to wireless, we exploit the use of polarization. And so not only do we have 7 cores, but we also have 2 polarizations per core. So there are actually 14 different sets of data that are running through this receiver, and we were able to complete this in real time. And the experiments we saw were quite remarkable. What I'm showing here are a comparison, but what you should really look at is the difference between the green curve and the red curve. In all cases, the green curve, which is the 7-core coupled core fiber, is better performing than an equivalent number of single mode fibers. So the comparison is you have a certain amount of information that you can send on a single mode fiber. If you multiplied that by 7 and just said that it was 7 cores and compared that to this 7-core multi-core fiber, is there an advantage in being coupled or having 7 individual fibers? And what we found is that there is an advantage. And then it was a bit of a surprising result, but we think we understand it now. But this coupling actually has an advantage. It reduces the amount of nonlinearity in the fiber because it's a larger mode within the fiber. And so there is tangible benefit in running multi-core coupled core fibers as opposed to many cores or many fibers. So there is a significant advantage. And the other challenge that we were concerned about relates to the MIMO processing is how stable is the coupling from one mode to the other. So the test here that we did here was on along a fiber length. I think it was 25 kilometers that is underneath the city in Italy. And so it's underneath the city, but you can sense traffic above. So there's definitely shaking of the city. And we were concerned that all that shaking of a city over that is above would cause a variation in that change in coupling between different modes, which would make it very hard to do this MIMO processing. But in fact, what I show here is that in fact it's quite stable. And so this really was, again, a remarkable result that showed us that this idea of being able to use these coupled core fibers, the same size fiber now as we have today, but now more than 7 times as much information over the single optical fiber. The second type of fibers that we looked at, just changing gears from coupled core fibers to multimode fibers. So many of you might have used multimode fibers. They're used very often in data centers, for example. They have a somewhat larger core. Sometimes they're made out of plastic, and so they're a lot easier to use because the precision of being able to align 2 fibers is a lot easier with multimode than single mode. And in a typical multimode fiber, you can support 45 or 55 different modes. And we were able to develop a multiplexer, which take at an input a single mode, a single dot of light out of a single optical fiber. And through a series of multiplane converters, these are phase plates, optical plates, we are able to convert from a single dot to each of the 45, in this case, modes directly. And so if we have information that comes in on the single mode optical fiber, we can then transform it into a given mode. And so if we had 45 single mode fibers, we could make all 45 modes and then place them into a multi-mode fiber together. And we do this often. Similarly, we can take these multi-modes that you see here at the bottom and transform them back. And so we can go from 45 different fibers into a multi-mode fiber, transmission over a multi-mode fiber, and then be able to multiplex them at the back end and be able to take them back to 45 single mode fibers. And so just to show, we've built the phase plates to be able to do these for all 45 simultaneously. The one back is fundamental. You see, we started at a single dot and get to a single dot, but all the different variants of modes are there. What we then did is we built a system. This particular one I'm showing you here, it was a post deadline 2 years ago. And here across both the C-band and L-band, we were able to transmit information on 2 different polarizations and 15 modes. So this wasn't 55 modes. This was 15 modes. And we were able to show the petabit per second, even after forward error correction that you need for protection of your link. Quite a remarkable over 100 bits per second per hertz. For those of you that know that metric, it's really, this was a world record result at the time. And assuming the post-deadline committee at ECOC, which is happening next week, this is the European Communications Conference, optical conference, assuming the post-deadline committee accepts it, you will be seeing another world record next week. So stay tuned for that. But we're very excited about the opportunity here with multimode fibers. So increasing speed, changing gears a bit. So changing speed, so increases in speed is needed, of course, in the transport, but is also needed in the access as well. And so in our teams, we also are looking at ways of increasing the speed for consumers to the home. Today, in many parts of the world, we're deploying 10 gigabit PON, or it's called XGS PON. Here at Nokia, we have solutions that we're selling primarily for enterprise at 25 gigabit PON, and we are in standards pushing and making available solutions for both 50 and 100 gigabit PON. So the applications that we expect to serve with 100 gigabit PON are less consumer, perhaps. We'll see. Maybe there's a need for consumers to need those sorts of speeds, but especially for enterprise applications. Think of backhaul for 5G or 6G access points in a very cost-effective manner. There's a benefit that we have in our design of the 100 gigabit FlexPON is similarly to what we did with probabilistic constellation shaping, which is the adaptation of how much information you can put over a fiber link to the quality of the fiber link itself. So rather than one size fits all, it's let's see what the maximum is I can give you and then try to give that to you. 100 gigabit FlexPON really does that quite well in several different ways. In this particular case, we're showing here by changing the forward error correction codes that are used, as well as moving from single BPSK to PAM4 encoding on the link. And this exciting new result, a very new result, did the first trials in Germany last year. And some of you may have seen this demo at Fiber Connect here in Nashville. This just a couple of months ago, where we won an award for that proof of concept demo. So with that, let me change gears again and talk to you about a second challenge that we see, and that's in processing integration. What I show here is a picture of not integrated circuit chips. It looks like the old DIP chips in the past, but these are the dates that a building was built in a data center farm that Google has in South Carolina. And you see there was one built in 2009, and 3 years later in 2012, and now 2 years later, 2014, 1 year later in 2015. You see there's an acceleration in the building of buildings that's happening there. This is mirroring the traffic demand that's coming, which is also exponential. And the challenge that this brings is rather fundamental. As I mentioned before, we have the per wavelength rate on a single fiber, a single color of light, but we have demand, which is driven by Moore's law. And so one of the challenges we're seeing that's evident in data centers is that the router blades that are made by router manufacturers like Nokia and Broadcom and others, the demand that they have is outstripping what we're able to provide on the single color of light. And so what we're facing now is we have 20 times the amount of information that we need to provide to a router blade itself. So we're building 20 terabit routers. There's talk about switches that are close to 50 terabit. that means you need to provide, 20 terabits or 50 terabits in, 50 terabits out. And so the amount of fibers that you need on the front panel to be able to do that are simply exploding. This is a problem. And the way it's been managed up to now is just by building more buildings and being able to spread things out in order to provide the routing in a distributed fashion. But that's not sustainable. So what we see is there is an essential need for a greater level of optoelectronic integration. It's essential for capacity, but it's also essential for cost, because as our customers, as the web scales and you in Internet 2 and the communication service providers are expecting orders of magnitude increase in the amount of information they send, they are not expecting to pay an order of magnitude more for that. In fact, I would argue they expect to pay the same, but for 10 times the amount of data, which is similar to the expectations of the consumer. So how are we going to address that capacity and cost? Well, it's through massive integration technologies. The integration technologies are also a must-have, because this is the only way that spatial division multiplexing can really address the scale problem, is if you scale in the implementation, the connection between all of those fibers and the processors or switches or routers that take that information and do useful things with it. Detailed integration and massive integration is absolutely essential. So what we are doing is, through new technologies, bringing new technologies to try to integrate to a greater degree. One of the challenges is in integrating together many different lasers. Typically, lasers are one at a time. You have one different laser. What we're starting to do on the left-hand side is use silicon photonics technologies to create, in this case, 16 different colors, all going into an optical fiber in a single monolithic package. And so it's basically a multiplication of the number of lasers by 16 in a single package. So that's one direction that we're going. Another direction that we're going here is on the right, is in the foundry that we have in our team. We're actually growing different lasers on silicon directly. So in this case, we have 5 different lasers at 5 specific frequencies, all grown simultaneously on the silicon wafer, for allowing this integration at the actual growth of the growth time. So the integration is not done post growth. It's actually part of growth. And so we see this as a very cost-effective way of getting to the levels of integration that we require. So very quickly, before I run out of time, I wanted to tell you about deterministic networks. So what are the attributes that we see as needing in deterministic networks as compared to the best effort networks that we have today? Well, the reliability needs to be significantly improved from where we are today, and I'll talk to that in a second. We need lower latency, especially lower jitter networks in the future, higher capacity, greater security. The geography is in many places in the world, particularly in Europe, there are government rules on where data can travel. It can't travel out of the country boundaries, so you need to be aware of that. We need these networks to be dynamic and proactive and flexible. And this is all in order to create what we see as the next wave, which is not only greater expectations from consumers for the learn from home, work from home, but also to enable industrial applications, which carry with them business level expectations, which are far higher than are needed to provide the voice or video or web surfing that we have basically built the internet to connect. The vast majority of applications are one of those 3. One of the ways that we're addressing this problem is by realizing that the telecom fibers that are in the grounds today are wonderful for providing an enormous amount of information from between 2 different points, but they also, using the same technologies, and in fact, even the same transponders, we can sense the environment nearby the optical fiber. And so you can think of the telecom fibers that are deployed all over the world and even under the sea as a massive distributed sensor. So fibers have been used for sensing for decades, so that's not new. But what we are seeing more and more is that the fibers that already are out there and already doing work providing telecommunication connections can also be used for sensing. And so some of the things you can do are to sense earthquakes or tsunamis. And so we're seeing a lot of interest in using that for prediction. We can sense the weather. We can sense if there is construction nearby the fiber. And this is interesting to us at Nokia because we'd like to have the ability to give a heads up to our customers that, hey, there's something nearby your fiber that you should be worried about. And so there may be a threat to your fiber. If there's time, we'd like you to take some action to try to make it so they don't cut your fiber. But that early warning of information means that you can do things like reroute on different optical fibers that go in a different duct that maybe aren't threatened by construction nearby. So that's the thought here. This is part of a larger effort, and that I'll expand upon, where we're using sensing to be able to sense the state of the network, the performance of the network, obviously the connections that they have, but also increasingly the challenges that we may have on different segments. So we take that telemetry from the network nodes themselves. We marry that together with information from other sources, the weather, for example. And if you do have the ability to add new types of sensors and new types of deployments, then fine, add that in, put that into a digital twin, a database, a data lake, which you then use with, in our case, hundreds of different analytics and optimization engines looking at this real-time image of the network itself, using these analytic engines to look for anomalies, look for problems, look for areas where you can do better, where you can go faster, and optimize, and then using that information to actuate the network in order to improve the performance of the network. So this is an exciting time with this, and really this automation is really the new disruption, the new inflection point that we're seeing in the optics area. So if you take an optical fiber and you look at the polarization on the optical fiber and you bend it repeatedly or you shake it, you can see very clearly that the polarization of light within the optical fiber changes. And so this is just a simple example of what happens when you take that. So we use this today in order to sense if somebody is in a rack playing around with the fibers, bumping them in a data center, for example. But in the real world, where fibers are either on spans, aerial spans, or buried in the ground in conduits, you're never going to see this level of changes in the polarization. But those changes are there due to acoustic noise that happens to be in the ground next to the optical fiber. So what we started to do with trials, and many trials that we've done, is looking at the polarization, or the Q factor in this case, on an optical fiber. And certainly we can see when amplifiers fail in the systems that we build today. The systems that we build today report back failures on about every 10 or 15 minute time scale. And so clearly we can see an optical failure, or if a rodent bites the cable and breaks it, or if you have a tree falling that you need to repair. But what we saw quite quickly is that all those signatures look almost identical, because we're only looking once every 10 or 15 minutes. And so what we realized, and that we started to look at trials, is we really need to look a lot faster. We need to look many times per second in order to be able to look at the changes in our network with a resolution to be able to interpret and predict and identify what type of threat might be present. At the same time, we also saw that there are new events that are happening in our network, which we had some inkling were happening. What I'm talking about is something that we are calling a Q drop. A Q is the quality factor, and so it's a abrupt change in quality. It's very short, less than a second. But less than a second, if it's 10 milliseconds, it's already blowing away packets on an optical fiber running at 1 terabit. So it's obviously something that is a problem that we need to solve. To be honest, we don't know what this is. We have seen it not only in data that we have taken on networks that we monitor, but we also see it in other networks that have been published, particularly the Microsoft data that was published several years ago of the network. So this is, stay tuned. If I'm asked to come back and give you an update, I may be able to tell you what is happening here. But these Q drops were sudden bursts where we have a challenge to the optical fiber links are something that are a problem. You would only see them if you sensed many times per second. If you average them over 15 minutes, we haven't seen them up to now. But this also is indicative of what we see in terms of the real reliability of networks. We rely very much because the applications that we are looking at, whether it's web surfing, video, or voice, are very robust to network outages and network failures, particularly short ones, where video buffers are huge. And so if the network goes away for 10 seconds, you and I probably don't even know. And so if you look at the actual reliability on a single segment or in a full connection between a path across many segments, in fact, the reliability, the number of nines of reliability is probably closer to 10 to the minus 2 to 3, as opposed to 5 nines of reliability, which is what we would like to get to at least. And some applications will demand even more than this. So the reality is today our networks, because of the applications that we are provisioning, are in fact not as reliable as we would like. We lean a lot on TCP/IP to do retransmission for those applications that don't require a strict deterministic connection or as much error protection as others. So this unavailability, this downtime does cost. We've done some calculations on what that is, and it can be quite substantial for if you're running it in a network that has significant failures. And we do see these types of networks in parts of the world, and certainly the reliability impacts their ability to provide service and gain revenue. The way that we have been protecting networks up to the past is through good design and building in redundancy. So 2 paths of redundancy for optical protection is a good way and will remain. It is the primary first line of defense. But the focus that we have been looking at is looking at reactive approach. So trying to fix failures as fast as possible. So if there is a failure, identify it quickly by sensing often and then rerouting quickly in order to react. But then the exciting new one that we're getting recent results that are exciting is proactive. So sensing that there may be a problem in the future, and so you should take action now rather than the future. And so in fact, in that case, there is no downtime. The availability is preserved. And so this is really an exciting, and this is the focus of the work that we're doing. So what I show here are some recent results of a trial that we're doing with a major web scale provider on a submarine cable, and it's illustrative in the pictures on the right of that trial. But we have 3 or 4 other trials looking at terrestrial links as well. what I'm showing here is, so the fiber goes from Virginia Beach to France, and along the line, we're seeing polarization changes, which we look at and can interpret their signature. In this particular case, we can tell this swell event here was during the set of 3 Atlantic storms that happened in July of in August of last summer, and so we saw them very clearly. These are the shaking of the waves at the top, with the fiber down several kilometers, at least under the water. So really extraordinary sensitivity that we have to see things that are at the surface level. As I indicated, we're able to use this technique for terrestrial. So we did some trials in Portugal as well. There we have, using the machine learning algorithms that we've now built up over several years of these trials and tests. I can tell you the difference between a fire and a rodent and a backhoe right next to the fiber, or an anchor that's dropped next to the fiber. I have a signature for a stiff wind. And so the signatures that you get by looking at the frequency patterns, the variation patterns of the polarization going in these along these different paths, is really quite unique. And so we can identify where an issue is happening and what it is happening with quite a remarkable sensitivity. So here we're using the fiber itself. So there's not new fiber, nothing new. It's fiber itself, in order to learn about the environment to protect the network, essentially. A second thing you can do is by using other fiber information that we have. So in the coherent detection, we need to look at chromatic dispersion in very real time in order to do the best possible performance on the optical networks. So what we have been able to do is to use that information that is already gathered as part of the coherent communication to be able to identify what types of fiber are where. This is crucially important because you maximize the amount of information on a link based on what type of fiber it is. And so if you don't know what type of fiber it is, and unfortunately sometimes the networks, we don't know what fiber is which. But by collecting and centralizing and then correlating the different paths that might go on different segments, we can detect and determine what type of fiber is on each of these links with great accuracy. So again, information that's already being measured that we're able to use in order to improve the network performance, improve the speed of the network, give visibility to the network to the service provider directly. So we have, as I indicated, this representation, digital representation of the network can be used for a myriad things. I've shown you 2, but there are at least 7 different algorithms and methods that we have developed in Bell Labs. We've transferred all 7 this year to the business, and so they are putting them up in the business products right now. So it's really a very, very rich area for opportunity. Machine learning is really providing extraordinarily valuable at identifying issues and then helping us to address them. So I've gone too long, I apologize, but essentially what I'd like to say is the pandemic has changed expectations of our network. I would argue that was already happening because of the transition towards more industrial applications. The key challenges we have are how are we going to continue to keep up with this 60 to 100% per year expectation of capacity growth, and how do we turn the best effort networks that we have today into deterministic networks of tomorrow. So with that, I thank you so much for your time and attention. I'm happy to take any of your questions.
Thank you, Todd. It's some very interesting things there. Yeah, so to all the attendees, if you have any questions, a reminder, you can put those in the Q&A portion of Zoom, and Todd will be happy to answer those. I do have one. You talked about the spatial division multiplexing and more fibers, whether it's coupled core or multimode. Clearly there's expense in that technology, rolling that out, or researching it and improving it and rolling that out. And so how do you expect that to begin to be commercialized, or when and how is that going to happen?
So I think there's two different areas where we're already seeing it happen. So one is in undersea connections, where the demand for undersea connection and capacity is exploding. And so we are already seeing the numbers of fibers that are in the cables that they stretch across the Atlantic and Pacific and around the Horn of Africa are increasing. So it used to be 12 fibers bidirectional, 12 pairs, so one in each direction, that were the standard and had been the standard for 25 years. We're now seeing people talk about 24 or 36, even 48 as potential futures. So I think that will happen. That is happening now. That there are growing, and Nokia has a division called Alcatel Submarine Networks, where we are exploring SDM and increasing in submarine. But the other place that we're seeing it is in traditional terrestrial deployments. So if you have a given fiber link that you want to put in, then the cost of the fiber itself is almost a minor cost of deployment. All the cost is in the civil engineering, it's in getting the lawyers to get you approvals to dig up the road, it's in getting the policemen to keep the traffic while you're digging it. It has nothing to do with the cost of the fiber itself. And so what we're seeing more and more, and the fiber providers are providing this, are people putting in enormous quantities of fiber if they happen to open up a new duct or a new path on beside a highway. They're not putting down 10 or even 100 fibers. People are now buying 7,000 core fibers. So those fiber providers have it. And so it's a big cable, but it has 7,000 fibers, and they put it in there because they too are looking at this 100% per year increase in growth, and they know they're going to use them someday. And they don't want to come back and dig up the road again late in the future. And so we're seeing more and more, particularly in customers that are extremely challenged on their capacity, is that when they are forced to deploy fiber, and everybody agrees it's a massive economic undertaking, when they do that, they're putting in massive amounts of fiber. So we're seeing it already, and we expect it to continue as more fiber is deployed.
It's interesting. I had no idea that you would even think about putting in, say, 7,000.
Yeah, it's amazing. It's amazing cable.
Very good. Well, thank you again. And in the interest of time, I think we need to wrap up. But appreciate you sharing all this great information. Very interesting. Thanks to everyone who could join us today. We hope you found it valuable and informative. And a reminder that we did record this event, and it'll be posted along with the slides on the i2 Online website. And if you have further questions about anything, feel free to reach out to us, and we can put you in contact with Nokia. Our next webinar will be on October 12th, when we will be joined by Tim Drake. Tim's a principal consultant within the optical division, and he'll speak on modulation and baud rate and closing the digital divide. So information on all our webinars is on the Internet 2 events page at internet2.edu/events. And again, thanks to you, Todd, and thanks to everyone who joined us today. Have a wonderful day.
Thank you.